Welcome everyone. Today we'll be working on continuity of the function. So first we are going to define the continuity of the function. So let's get started with the definition of the continuity of the function. A function y equal to f of x is continuous at x equal to a. So if you have a function, any function y equal to f of x, let me draw it here. Suppose this function is y equal to f of x. If I want to check whether this function is continuous or not at a given point, say for example at x equal to a, okay, if I want to check whether this function is continuous at x equal to a, the function will be continuous if there is no break. There should not be break in the function over there. Like here, there is no break. No hole in the function. When I say break, break may be like this. Let me draw here. If I say break, maybe the break is like this. From here, the function is going up to here. There is a break and is going from there. This is a break. But if there is a break, function is not continuous. There should not be break. There should not be hole. When I say hole in the function, it is like this. There is a hole like this, and the function is going like that. That's a hole. This is a break. This is a hole. There should not be break. There should not be hole, or there should not be any kind of sharp corner. When we say corner, it is like this. Function is going up like this, and then making a sharp corner, it's going like that. This is the break, this is the hole, this is the corner. If the function has a break, hole, or corner, it is not continuous. If nothing is there, the function is continuous like this. Mathematically, we say that the function is continuous if the limit of the function is equal to value of the function. That is very important for you to note. You can circle this one in your note catcher. If the limit of the function is equal to value of the function, then the function is continuous. So if you are checking whether the function is continuous or not, we check these three conditions. The first one is we check whether the function is defined at a or not. You must be able to find the finite value of the function. When we say function is defined at a function must have finite value. Function must have a real and finite value. Okay, if a function has a real value, not an imaginary or real value, and a finite value, not infinity, then we say that the function is well defined. Next one is the limit of the function must be exist. You must be able to find the limit of the function. And the third and very important condition is the limit of the function must be equal to the value of the function. Limit at a must be equal to the value of the function at a. Here are some cases. So let's check this. The first one you can see, if you look at the first one, this function has a break. So this is not continuous. And the reason is you can see you cannot find the limit. When you go from the left and when you go from the right, you don't go to a same value. So this second point is not true. There is no limit of the function at x equal to a. This one, the value of the function is not defined because if you look at a, the function is going to infinity. It does not have a finite value. Instead, it has infinite value. First condition is not true. That is also not continuous at a. The third one is not continuous at a because there is a hole. Meaning of that is, if you want to find f of a, what is f of a? It is not there. F of a is not defined. It's not a continuous function. This one, the limit of the function, if you look at this function, the limit of the function is L, but the value of the function is M. So this is not continuous. But the last one here, this will satisfy all conditions. You have the value of the function, the limit is equal to L, the value of the function is also L. So the last one is continuous function. So this is the basic idea about the continuity of the function. Example, determine the point of discontinuity. You have to look at this graph and then you have to tell where the function is discontinuous, and you have to tell what type of discontinuity is that. So what we are doing is we are writing two things here. Let me make a table. We are looking for the discontinuity point. Where is it? Where it is discontinuous. I'm going to call it discontinuity point. And also, by looking at the graph, you also need to tell what type of discontinuity is that. So type of discontinuity. Okay. Now, let's answer this question. If you look at this graph, you can see that there is discontinuity at x equal to 2. The function is not continuous at x equal to 2. So x equal to 2, there is discontinuity. And what type of discontinuity is this? You can see there is a break in the graph. Whenever there is a break in the graph like this, the type of discontinuity is called the jump discontinuity. It is called jump discontinuity. That is the first one. Similarly, if you look at this x equal to 3, the graph is discontinuous because when you go from left, the graph is going all the way to infinity. From the right also, the graph is going all the way down to infinity. And there is a break in the graph. Okay, the graph is discontinuous here. So this discontinuity, which is caused by the value of the function going to infinity, it is called the infinite discontinuity. Infinite discontinuity. This is called infinite discontinuity. Now you will see one more discontinuity here, that is at x equal to 4, and there's a hole there. So it is at x equal to 4. Here the limit of the function from both sides when you go, the limit is 4. But the value of the function is down here, which is 2. That means if we move this dot up here, we can remove that discontinuity. So this type of discontinuity which can be removed, it is called removable discontinuity. Removable discontinuity. Okay, that is removable discontinuity. Example, are the functions given below? There are two functions given here. Continuous at a, here a is equal to 1. And the second one, that is your a or x is equal to 1. Use the continuity checklist to verify your answer. So in part A, let's see what we have. First, let's try to find the value of the function f of a, or the value of the function at a. So a is 1, so I want f of 1. F of 1 equal to the value of the function at 1 when x equal to 1 is equal to 2. So the first condition is true. The function is well defined. Next, we have to find the limit. Limit as x approaches to a, and value of a is 1, of the function. When x approaches to a, this is our function, which is x squared plus 5x plus 6 divided by x minus 1. You can see here, if you try to plug in 1 in the numerator, 1 is squared plus 5 times 1 plus 6, that will be 12. And when x approaches to 1, when x gets closer and closer to 1, this value will be closer and closer to 0. Meaning of that is this is very small. When you divide a finite number 12 by a small number, this is going to be infinity. because it is 12 divided by very small number, which is infinity. So that is your limit. Now you can see the first condition is true, the function is well defined. Second condition is true because we are able to find the limit. But if you look at the third condition, the value of the limit and value of the function are not equal. Now, the limit as x approaches to 1 of the function and the value of the function at 1, they are not equal. All three conditions must be true. This is not true. Okay, this is not equal. So meaning of that is this function is not continuous at x equal to a. So the conclusion will be f of x is not continuous at x equal to 1. If all three conditions were true, then we say that the function is continuous. But here, all three conditions are not true, so this function is not continuous at x equal to a. Now, let's look at part B. Our function is f of x equal to square root of x minus 5, and we have to check whether this function is continuous at x equal to 1. Let's try to sketch the graph of this function so that it will be very clear. So let me draw the graph. You can also draw the graph. This is the square root function shifted 5 units to the right. So when you draw the graph, your graph will be like this. This is the graph of f of x equal to square root of x minus 5. If you are not comfortable in sketching the graph without using calculator, you can use your calculator to check the graph and then you can sketch it like this. So this point will be 0, 5. I mean 5, 0. X is 5. 5, 0. Now we want to check whether the function is continuous at x equal to 1. 1 is here. At x equal to 1, we don't have the function. So logically, we cannot say that the function is continuous at x equal to 1. But we are going to use our checklist and then find out whether the function is continuous at x equal to 1. Because at x equal to 1, we don't have that function. So let's try that. First, we want to find the value of the function at 1. If you try to find the value of the function at 1, to find the value of the function at 1, here the value of the function at 1 is not given, so you have to plug in 1. So it will be square root of 1 minus 5, which is equal to square root of 1 minus 5 is negative 4. That is 2i. You can see the value of the function is not real. This is not real. Here, f of x is not defined. Not defined at x equal to 1 because the value is not real. So since the function is not defined at 1, this function is not continuous at x equal to 1. So f of x is not continuous at x equal to 1. So we have to determine the interval on which this function f of x equal to x squared minus 4x plus 3 divided by x squared minus 1 is continuous. So let's begin. F of x, which is the rational function, that is the function in the form of a fraction, is defined if the denominator is not 0. If the denominator is not 0, because in a fraction, denominator cannot be 0. So this cannot be 0. Now, what is the meaning of that? Let's try to solve this one. Let's do some side work. So when I have x squared minus 1 not equal to 0, and if I try to solve this, let me add 1 on both sides. X squared not equal to 1. Now take square root on both sides. Then you get x is not equal to plus or minus 1. So x cannot be positive or negative 1. So I can write this implies x cannot be plus or minus 1. The meaning of that is if you plug in 1 or minus 1 in the denominator will be 0. Because 1 squared is 1 or negative 1 squared is also 1. 1 minus 1 is 0. So in that case, the function will be undefined. But for everything else, the function is well defined. So meaning of that is our function is well defined from negative infinity up to infinity, except at negative 1 and positive 1. At negative 1 and positive 1, at negative 1 and positive 1, the function is not defined. And you know that if the function is not defined, it is not continuous here and here. So f of x, I can write f of x is not continuous at x equal to plus or minus 1. It is not continuous here, and also it is not continuous here. But everywhere else, the function is continuous. The meaning of that is the function is continuous here, the function is continuous here in that interval, and also here in this interval. Our question is to determine the interval on which the function is continuous. Function is continuous in this interval, and in this interval. So we can write f of x is continuous on this first interval here, which is from negative infinity up to negative 1, but negative 1 is not included. So we write like this, negative infinity up to negative 1. Negative 1 is not included, that's why parenthesis. And also from negative 1 up to positive 1, negative 1 up to positive 1, and from positive 1 up to infinity. From positive 1 up to infinity. And if we want to say all these three intervals together, we put the union sign in the middle, which is like U, like that. So we can say that this function is continuous on these three intervals because it is not continuous at these 2 points. Example, let f of x equal to, it is a function, again it's a piecewise defined function. It is 7x minus 1 when x is less than or equal to 10, and then negative 5x plus b for x is greater than or equal to 10. Now, we have to find the value of b if the function is continuous everywhere. But here is a break at 10, you can see. So for the function to be continuous, okay, this is a linear function, it is continuous everywhere. This is a linear function, it's continuous everywhere. But if you look at the end point, that's at 10, that's where we have to be careful. So this is how I'm going to begin. For f of x to be continuous, the first function, I'm going to call it y1 equal to 7x minus 1, 7x minus 1. And the second function, I'm going to call it y2, which is negative 5x plus b, negative 5x plus b. They must have same value, must have same values at x equal to 10. Okay, these two functions must have same values at x equal to 10, and they will be continuous. So if they have same values, that is when you plug in 10 to this function or 10 to this function, they must be equal. So if you plug in 10 here, it will be negative 5 times 10 plus b is equal to, if you plug in 10 there, 7 times 10 minus 1. We are asked to find the value of b. We have an equation. Now we can easily find this. So this implies negative 50, because negative 5 times 10, negative 50, plus b is equal to 7 times 10, that is 70 minus 1. Now, if I add 50 on both sides, it will be b equal to, if I add 50 here, that will be 120 minus 1, which is 119. So that is the value of b. So meaning of that is, if the value of b is 119, this function will be continuous. Otherwise, the function will not be continuous.